Today I'm visiting the Glasshouse Crops Research Institute at Littlehampton in Sussex. This is one of the many experimental stations run by the Agricultural Research Council to find the best conditions for the commercial growing of various vegetables and cereals. Here they concentrate on crops that are usually grown under glass commercially, such as tomatoes and lettuces. But they do have some outdoor experiments here as well, such as this experiment on rhododendrons, where various different soil additives are being tested. And these Elwoodii conifers show very clearly the effects of adding different amounts of potash to the soil. But the main experiments here take place in glasshouses, so let's go and have a look at one of them. You can see how they use frosted glass on the south, east and west walls of this glasshouse. Now let's take a look inside. The frosted glass that you saw on the outside of the house diffuses the sunlight, so that the plants growing on the southern side don't get any brighter light, and the guttering doesn't cast any shadows on the plants. This square of land here is a plot, and you can see how 3 samples of the crop have already been harvested from it. Now, every effort is made to make sure that the plots of land inside the glasshouse are as alike as possible, but it's impossible to make them completely alike, and one reason for that is the heating, which is provided by these pipes. Some plots are nearer the pipes than others, and so there's a temperature gradient down the length of the house and also across the width of the house. So the experimenters have to allow for variability in 2 directions. Now, how do they do this? Well, we've seen in Unit 6 that a Latin square is one answer to the problem of having plots which vary in 2 directions. And indeed, if we look at the growing plan that they have for the house, we find here a 3 by 3 Latin square. There are 3 varieties of lettuce, and each one occurs once in each row and once in each column. Now, this particular experiment is to test various different growing conditions on 3 varieties of lettuce. There are 4 different amounts of time during which extra carbon dioxide is pumped into the house, and 2 different minimum daytime temperatures. That makes 8 different environments in all, and so 8 glasshouses are used. Just within this particular glasshouse, carbon dioxide is added for 100% of the daylight hours, and the minimum daytime temperature is 13 degrees centigrade. Now, within each glasshouse, all 3 varieties of lettuce are used, so let's just concentrate on this one glasshouse. The plan shows this 3 by 3 Latin square, and here's the Latin square on the ground. You've probably noticed how we've marked off the boundaries between plots with this white ribbon, which shows the plots more clearly. And then you can see that the lettuces growing in this plot here are different from the lettuces growing in the neighbouring plot. But each variety occurs once in each row and once in each column, and so realistic comparisons can be made between the varieties. Well, that's all very well, but actually we know that the glasshouse isn't square at all. It's long and thin. And you probably had noticed that we ignored part of the growing plan before. We only looked at part of the plan, a single Latin square. And of course, the whole plan takes account of the fact that the glasshouse is long and thin. It consists of 3 Latin squares, each with the same 3 varieties in.
In practice, experimental plots are far more often laid out in a rectangle than in a square. So we need a technique for constructing designs in rectangles. Let's have a closer look at how that glasshouse design was built up from Latin squares. Well, we know how to use a Latin square for a 3 by 3 layout with 3 varieties, like this. But suppose that we have a layout 3 plots wide and 6 plots long. Well, we start by taking our Latin square and putting it on the first 9 plots, like this. And then for the remaining plots, we take another 3 by 3 Latin square, like that. Now, this could be the same as the first square, or it could be different. It really doesn't matter. Notice that each variety occurs once in each column and twice in each row. And if we had 3 varieties to test in a longer layout, then we could go on doing this, using Latin squares all the way down. But plant breeding experiments are rarely as simple as that. There's normally more than 3 varieties to compare. Suppose we have 6 varieties. How do we proceed then? Well, first we divide both the length and the width of the house into 3. That gives us 9 rectangular blocks, each containing just 2 plots. Then we divide the 6 varieties into 2 groups of 3. Here we've called the varieties in the first group A, B and C. And those in the second group alpha, beta and gamma. We first want to place varieties A, B, C on half the plots, 1 plot from each block of 2. So we've got 3 varieties and the 9 blocks are in 3 rows and 3 columns. So the obvious thing to use is a Latin square. That puts one of A, B, C into each block, and each variety occurs once in each row and once in each column. Now for the other 3 varieties, alpha, beta, gamma. We'll put one of these in each of the remaining plots and we'll use the same technique. So we must first write a 3 by 3 Latin square using alpha, beta, gamma. And then use this to put one of alpha, beta, gamma into each of the remaining plots. But now look what's happened. Each of the 3 blocks containing A also contains alpha. So A and alpha occur in the same block 3 times, and A doesn't share a block with anything else at all. This is highly unsatisfactory in the design. It would be much better if the 3 blocks containing A could contain each of alpha, beta, gamma just once.
So let's see if we could choose the Latin square for alpha, beta and gamma in a better way, so that we get a more balanced design. Let's start off by putting alpha, beta and gamma in the top row, like this. Now, this A comes with an alpha, so we'd like these 2 A's to come with a beta and a gamma. But we can't have a beta here because we've already got a beta in this column, so we'll have to put beta and gamma in like this. Now I'm going to copy those positions of beta and gamma onto the little square above. So there's gamma and there's beta. Now I want to try and complete this square above to make a Latin square. This column needs an alpha, and then the bottom row needs a gamma. This column here needs a beta, and finally we need an alpha in this row. And now we can copy these positions of alpha, beta and gamma back onto the bottom diagram. So beta comes down like that. Here's a gamma, and then the other 2 positions are both alpha, filling in like so. And now look, the blocks containing B contain alpha, beta and gamma, and the same is true for C. So every Latin letter occurs just once with every Greek letter, and so this is the best design we can hope for. The 2 squares we've got here obviously bear a very special relationship to each other. They have the property that if you choose one square, choose any letter of that square and look at the positions it occupies, those positions in the other square have every letter exactly once. When we have 2 squares like this, we say they are orthogonal to each other.
Here's the formal definition of orthogonal Latin squares. 2 Latin squares are orthogonal if each letter of one square occurs exactly once with each letter of the other square. Look at these 2 squares. Rosemary has just shown you that they are orthogonal. Now let's put them together like this. You can easily see that each Latin letter occurs just once with each Greek letter. Now there's one thing I want to point out here. If you look up in reference books or tables, you won't find many Latin squares written with Greek letters. But we can still check for orthogonality even if we have 2 squares with the same symbols, because the definition doesn't say that the symbols in the 2 squares must be distinct. So we don't have to use different sorts of letters for the 2 squares. Looking back at this example, over here we have a Latin square, which uses Latin letters, but apart from that is exactly the same as the Greek one. Alpha's been replaced by A, beta by B, and gamma by C throughout. Now, if we put this square together with our original one, like this, we can see that each pair of Latin letters in each order occurs exactly once. Here's AA, AB and AC, and here's BA, BB and BC, and so on. So these two squares are still orthogonal according to the definition, and we can see that it doesn't matter what particular symbols are used in them. Now let's look at some 4x4 squares, which we shall be using later in the programme. These squares are on the Latin square cards we sent you, and they both use Latin letters. These labels 2A and 2B are also on the cards, so you should be able to find them easily. And if we put them together like this, you can see that each ordered pair of letters occurs just once. For example, AA, AB, AC and AD. And you can check the rest for yourself later using your cards. So the Latin squares 2A and 2B are orthogonal. But suppose instead of square 2A, we use this square, square 1. Now we put them together, and we get AA, but AB occurs twice, here and here. Now that ruins it. We've got the pair AB twice, so our definition tells us that these two squares, 1 and 2B, are not orthogonal to each other.
Chris has shown us how to recognise when pairs of Latin squares are orthogonal and when they're not. Let's recall why we wanted to use a pair of orthogonal Latin squares. We have a glass house which is twice as long as it is wide. Say 4 plots wide by 8 plots long, with 8 varieties. First we divide both the length and breadth into 4 pieces. Then we divide the varieties into 2 groups of 4. A, B, C, D, and alpha, beta, gamma, delta. Now we need a pair of 4x4 orthogonal Latin squares. We'll use squares 2A and 2B. Both squares are in the letters A, B, C, D. We want the first square to be in A, B, C, D, so that's all right. And because there are 8 varieties, we want the second square to be in alpha, beta, gamma, delta. So we replace A by alpha, B by beta, C by gamma, and D by delta. We use the first square to put in varieties A, B, C, D, and the second square to put in varieties alpha, beta, gamma, and delta. Now each variety occurs once in each row and once in each column, and each pair of varieties occurs together at most once. So this is a good design for a glass house which is twice as long as it is wide. But suppose it's 3 times as long. Suppose I have 12 varieties to fit into a 4 by 12 glass house. Well, here you can see I've started to construct a suitable design, and I'll show you what I did. First of all, I divided the glass house into 16 blocks in the usual way, and then divided the varieties into 3 groups of 4. Now for these first 2 groups, I took a pair of orthogonal Latin squares and used those to fill in 2 plots in each block in the usual way. Now, for this last group, I need a Latin square, and in order that no 2 varieties ever occur in a block together more than once, I need this new Latin square to be orthogonal to the ABCD Latin square and also orthogonal to the alpha, beta, gamma, delta square. Here's a suitable square, and I use it to put in the remaining varieties in the same way. So that's 1, 2, 3, 4, 4, 3, 2, 1, and so on in the way we've seen before. So I need 3 Latin squares with the property that every pair of squares is orthogonal. We call this a set of mutually orthogonal Latin squares.
So here's the definition. A set of Latin squares is mutually orthogonal if each pair is orthogonal. This is a straightforward extension of the basic definition of orthogonal Latin squares. We just need to check each pair from our set. For example, let's go back and look at some of the 4x4 Latin squares on your cards, squares 2A, 2B and 2C. We've already seen that square 2B is orthogonal to square 2A. You can also check that square 2b is orthogonal to square 2c, and that square 2c is orthogonal to square 2a. Since all three possible pairs of squares are orthogonal, we say that this is a set of mutually orthogonal Latin squares, or that these three squares are mutually orthogonal. And you should now be able to check whether the squares labelled 1, 2b and 2c form a mutually orthogonal set. An important area of research in this country is in the commercial production of fruit, such as pears and plums, when they're grown in orchards. Now, an orchard usually has its trees in neat rows and columns, and so a Latin square is often just the right thing. But trees do have one big disadvantage as far as experimental work is concerned. They take a long time to grow and are too expensive to be used for an experiment in just 1 year and then chopped down. So the same trees may be used for different experiments in successive years. In 1985 we could test different types of pest controlling spray on the trees. Then in 1986 we might want to follow this with an experiment on different pruning methods. But in 1986 the trees are very likely to still have some residual effects from the 1985 spray treatments. So if we want to investigate the pruning methods independently of those residual spray effects, then we must ensure that the trees which receive the same type of spray, between them have all the different pruning methods. Now, what we need to achieve this is a pair of orthogonal Latin squares. One for the sprays and one for the pruning methods. Now, although this arrangement on trees looks very similar to the arrangement we saw before in a glasshouse, their interpretations are completely different. In the glasshouse, we wanted to compare 6 varieties of lettuce in a single experiment. And so here, A alpha denotes varieties A and alpha growing in neighbouring plots. In the orchard, we want to compare 3 spray treatments in 1 year, and the next year to compare 3 pruning methods independently of any residual effects on the sprays. So now A alpha denotes a single tree which receives spray A in the first year and pruning method alpha in the second year.
If Latin squares were used only for row and column designs, it would hardly have been worth introducing them to you, because over 90% of agricultural experiments are laid out just in straightforward blocks. This experiment on fungicides for anemones is laid out just in blocks. Here each pot is a plot, and each group of neighbouring pots together on the bench forms a block. The bench is sufficiently narrow that we don't have to worry about variability in this direction, so we've just got the one system of blocks. In the unit I've explained why it's often useful for a block design to be resolvable. That means I can split the blocks up into replicates like this. A replicate contains each variety just once. I've also discussed the concurrences of pairs of varieties. That means the number of times that pair of varieties occurs in the same block. If there aren't many replicates, the average concurrence is likely to be less than 1. And in that case, we've seen that it's better for all concurrences to have values 0 or 1, rather than to have any of 2 or more. Then we call it a 0-1 design. So we'd like a resolvable 0-1 design for this experiment, and we can use Latin squares to help us construct one. We've just seen that what we want is a resolvable 0-1 design. I'll show you how to construct one for 16 varieties in blocks of size 4. The construction I'm going to use works only when the number of varieties is the square of the block size. Now, since there are 16 varieties and 4 varieties per block, the number of blocks per replicate is 16 over 4, which is 4. And here you can see the 4 blocks in the first replicate. Let's do 4 replicates, 1, 2, 3, 4, and then we have a total of 16 blocks. To construct the design, I first call the varieties by the numbers 1 to 16 and write them out in a square array. This array is not the design, it's just a device to help us construct it. Now, for the first replicate, I take as blocks the rows of this array. So the first block is 1, 2, 3, 4. The second is 5, 6, 7, 8. The third, 9, 10, 11, 12. And then the fourth row, makes the fourth block. At this stage, the design isn't even connected, because there's no way of comparing varieties 1 and 5, even indirectly. So we go on to the second replicate, and now we use the columns of this array, so that 1, 5, 9, 13 is the first block, 2, 6, 10, 14 the second block, and so on for the third and fourth blocks. Now the design is connected. For example, look at varieties 1 and 11. We can compare 1 with 3 in the first replicate and 3 with 11 in the second replicate. And so 1 and 11 can be compared indirectly. At this stage, all concurrences are 0 and 1. If two varieties occur in the same row or in the same column, then their concurrence is 1. Otherwise, it's 0. For the third replicate, I need a Latin square. Here's Latin square 2a. Again, this Latin square isn't the design, it's a constructional device. Now, for the first block, I take the letter A and pick out the varieties that occur in those positions, 1, 6, 11, 16, giving that for the first block. For the second block, I do the same thing with letter B, 2, 5, 12, 15. The third block is letter C, 3, 8, and so on. And then the fourth block is letter D down that diagonal. Now, because each letter just occurs once in each row and once in each column, if any two varieties concur in this replicate, then they didn't concur in the previous two replicates. So we still have a 0-1 design. For the fourth replicate, I take another Latin square. It has to be orthogonal to the first Latin square, so here's square 2b, another constructional device. And we use it in exactly the same way. First block A, 1, 7, 12 and 14. Second block B, 2, 8, 11, 13. Third block C, 3, 5, 10, 16. And letter D gives the remaining varieties in the fourth block. Now, because this is a Latin square, the argument we've just been through shows that if any two varieties concur in this replicate, they didn't concur in either of the first two replicates. And if they're in the same block here, then they're on the same letters of this square, and because these two squares are orthogonal, they're on different letters of that square, and so they're in different blocks in the third replicate. So we've still got a 0-1 design. Now if I just move these over and bring down copies of the first two replicates, you can see there the 4 replicates making the completed design. And of course, if I'd used a third Latin square orthogonal to the two I used, I could go on to construct a 5th replicate without destroying the 0-1 property.